Hey, what's going on, everybody? I want to go over LeetCode question 64, minimum path sum. You're given an n by n grid filled with non-negative numbers. Find a path from top left to bottom right, which minimizes the sum of all numbers along its path. And you can only move either down or right at any point in time. So if you look at this diagram, we're starting at the upper left corner. We start by going in the right direction, and then we head all the way down. So this is our minimum path sum. If we add all of these together, then you get 7. So that's basically the description of the problem. And I'm going to go over to whiteboard and kind of draw out what's going on. So let's get a red pen. We start at some origin 0, 0. And then we have two decisions to make from here. We can either go down to 1, 0, or we can go to the right at 0, 1. So at any point in time, whatever cell you're at, it's split into two different subproblems. If we decide to go down, then we have to decide, are we going to go down to 2, 0, or are we going to go down to 1, 1, right? And each of the cells that we're visiting has two different subproblems associated with it. And when I think of subproblems, I think a lot about recursion, because the same logic is applied to each of these cells. We can break it down using a recursive function. So let's formalize this to I and j, representing the row and column values. And this is going to be I, j plus 1. And then this is going to be I plus 1, j. Okay? So what we have to do is compare the values. If we add 1 and 1, we get 2. If we add 1 and 3, we get 4. Right? So far, the minimum path sum is going to be 2 because we want to choose the smaller of those sums. Okay? And now we want to see, okay, currently this is 2, so we can just mark this as a 2. Now, is 2 plus 4 greater than 2 plus 5? No, it's actually less than, so we're going to continue going down and add 4 to the sum. So instead of 4, this now becomes 6 because we added the 2. And now the only direction to go to from here is right, so then we make this 8 because we add 6 to 2. And then this is going to become 9. Okay, so splitting each of these cells, starting from I plus 1j, into two different subproblems, we found that the minimum path sum, if we go down, is 9. But we're not done yet. We have to compare that to the second subproblem starting from the origin, which is I, j plus 1. Okay, so now if we decide to go right, this is going to become a 4 because you're adding 1 and 3. And then we have to decide, is 4 plus 5 less than 4 plus 1? No, 4 plus 1 is less than, so we're going to go right. This becomes 5, and then we go down over here. The only direction to go down, 6, and this is going to be 7. So we actually didn't change the value of this 1. We just made it equal to whatever the sum was of this path. But now we see that we have two different values, so 7 and 9. From the origin, obviously we're going to pick 7 because it's the smallest one. All right, so if we have some helper function, let's just call it f, and we're going to pass in the grid. So this is a 2D grid. And we're going to pass in the row value and the column value. And like I said, we're splitting this into two different subproblems. So we want to branch this out to two different recursive calls. So grid I plus 1 j and f grid I j plus 1. So this is the right and bottom direction, okay? And from here, we want to set the current cell value we're at equal to the minimum sum. So in this case, if we start at 1, we want to see, okay, we want to make this equal to whatever the minimum path sum is between the direction we go to, right, or the direction if we're going down. And this just all bubbles up until we get to the end, and this is our base condition once we reach I is equal to the length of the rows and j is equal to the length of the column, so the bottom right corner. Okay, let me write some code and explain this a bit further. So like I said, we want to return some helper function. Let's just call it helper. We're going to pass in the grid, and we're just going to pass in the origin. Okay, and we're going to define our function to be an integer because we want to return the sum, the minimum path sum at each cell. And it takes in a 2D grid. It takes in an I value for the row and a j value for the column. Okay, as always for every recursive function, we need a base case to terminate the recursive calls. So we know we need to stop running the recursion once we reach the bottom right corner. Okay, and that's when I is equal to grid.length minus 1, and j is going to be equal to grid at index 0.length minus 1 for the columns. And from here, all we need to do is just return the value that it holds. So that's going to be at grid I, j. Okay? Otherwise, we have some recursion to do. And the thing about matrices that are a little bit complicated or interesting is that we have edge cases, quite literally edge cases. If we're at the bottom left corner and we know we can either go down or right, we need to compute the minimum between those. But what if there's no value in the bottom in this case? So we need to be a bit more clever of how we decide which way to go. So let's assume that we're at some bottom left or, top right corner, and we're going to just say int right is going to be a max value, and the same thing for down. Okay, so the same thing for down. The reason why is because if you compute the minimum value between some very large number and whatever value we do find, either right or down, we're going to choose the direction that obviously has the value. And we can confirm this if we look at the constraints. Each value can only be between 0 and 200. And max value is like 2 to the 32nd power or something like that. Okay. And now here's where we actually do the recursive calls. So let's see. So this is to see if we have a value to the right. So if we have a value to the right, that means j is less than columns.length minus 1. So if j is less than column length minus 1, then we do the recursive call for that right cell. So we say right is going to be equal to the helper function. We pass in the grid. I stays the same, except we increment j because j plus 1 is going to be the cell to the right of where we're at. Okay? And the same thing if we have a bottom value. And we know we have a bottom value if I is less than the length of the rows minus 1. So over here. So if I is less than grid.length minus 1, then we can say down is equal to helper grid I plus 1 and j stays the same. Okay. And now we need to compute and return the minimum sum, or minimum path sum. Right. So now we need to return the current value at the cell we're at, so grid I and j, plus the minimum of right and down. Okay? And let's run this and see if it works. So the test cases work, but I'm going to show you something a bit interesting if we hit submit. Notice how it's taking a really long time. There's actually a time limit exceeded exception because there's so many recursive calls being done here. It's going to be a large time complexity. So let me just clear this real quick. And let me copy this. Okay, if you think about how many recursive calls we're doing, this is broken into 2, this is broken into 2, you know, this is broken into 2, etc. It's going to be O of 2 to the m plus n power. And that's a very large time complexity. And the reason why it's this is because 2 is describing, you know, the different branches that we're making. We're going to 2 different paths. And because we're going through each of the cells, that's going to be m plus n, right? One way to fix this is to actually cache. There's a technique called memoization that caches the recursive calls so you don't have to do it every time. So this is a new technique. It's called memoization. Okay. So let's see, let me erase this. If we use memoization, every recursive call that we make, if we find the minimum path sum between this cell, we don't have to compute it again. So each time, if we're comparing the recursive calls and we want to find the minimum, we can already retrieve it from some dictionary or from some array because it's already been computed before, right? So if we have a cache describing the recursive call for each cell, we can just make it a 2D array. So we're going to make this a 2D array. And if we pass in our function, our recursive function, grid I, j, and then now we're passing in cache, what we're going to do is first check if there's a value in the cache. Because we can have values that are 0, we're just going to initialize our cache grid with -1 because there's no reason a value can have that number. So if the cache exists, so we can just say if cache ij, then we don't have to compute the recursive call for it because it's already been found. All we need to do is add whatever comes in the cache with the value of the grid that we're at, right? Else, then that's where we actually have to do the recursive call. So you would say like cache at ij, and that would be equal to, you know, the min right down, okay? And this is the only time that we're going to compute the recursive call for that cell. We're never going to have to do it again. So let me try to make it a little better here. So the first thing we're going to do is create a cache, and we're just going to call it cache, and it's going to have the same dimensions as the original grid. So grid.length and the length of the columns. Okay, and we're going to initialize it with like null values or just all negative ones. So okay, we'll just say cache a plus plus, and then now we loop through the columns to make 0 cache 0 dot length j plus plus. So we're going to initialize it to -1. Okay. Say okay. So now we have our cache array. And now we want to add it to our function because we need to look at values in our cache to see if it's necessary to compute the recursion for this cell value or cell index. Okay. And we're going to type in cache. Okay. Same thing applies for our base case. Once we reach the bottom right corner, we're going to return. But from here, this is where we need to decide if recursion is necessary. So if cache at our current index is not null or not equal to -1, then we simply return that value, like I said, because we don't need to compute the recursion. Okay. Okay. And just to make it more clear, I'll put an else statement. And compute recursion add to cache. And then here, cache exists. Okay. So from here, we're gonna do almost the same thing. We're just gonna put in here just to make it more clear. And let's just indent this a little better. Okay. So we look for our right and down values. Same thing here, right? You know, we compute grid at index ij plus math.min right down. The only thing is we need to set the cache equal to this and then return it. Because if we're only returning this value, then we still have to compute whatever recursion. We're going to have to do it every time. So we have to set cache at ij. We're just going to copy this. Okay. And then all we do is return cache from here. Okay. So add new cache and return. Okay. So let's run this and see if I didn't miss anything. Right, helper, okay. Oh, I see. I forgot to add the cache to these calls here. Okay, let's see. Okay, test cases work. Now let's submit it. And now we see that we actually have an accepted result. And the reason why is because our time complexity went from O of 2 to the m plus n power to just O of m times n, which is a pretty significant improvement. So without memoization or cache, time is O of 2 to the m plus n power. And then, but with memoization, this goes to m times n power. Okay? And the reason why is because we compute it once for each cell and then that's it. This is a really good way to, simplify your recursive problems, improve the time complexity, because it significantly reduces the recursive calls. So this can be applied to problems like the Fibonacci sequence, maybe some DP problems like house robber, things like that. Pascal's triangle can potentially be used, memoization can be used. So hopefully this helps you in your recursive problem solving. I know it definitely helped me. So thanks for watching, and I hope to upload more videos. Thanks.